Hello and welcome to the S Chemistry lecture series. In this video we're going to look at chapter 18 section 4, which is going to look at a different reaction of aldehydes and ketones, which is nucleophilic addition with hydrogen cyanide. Now with this reaction, it's going to be very similar to the electrophilic addition that we saw with the alkenes, but the reactions are going to focus around the carbon-oxygen double bond instead of a carbon-carbon double bond. So let's look at this. Nucleophilic addition with hydrogen cyanide is going to essentially create a two-functional group of product, which is what we call a hydroxynitrile. So this is going to happen anytime we grab an aldehyde or a ketone, so a carbonyl group compound. So if we react an aldehyde or a ketone, and I should say this is not and, this is or, so or a ketone. So both of these functional groups are going to undergo this reaction if they are reacted with hydrogen cyanide or HCN. So whenever our hydrogen cyanide reacts with a carbonyl containing compound like aldehydes and ketones, we are going to get a reaction that creates what is known as a hydroxynitrile. Now, hydroxynitriles is a very interesting compound because it has two functional groups. It has the hydroxy functional group, which is essentially an alcohol, an OH, and it's going to have the nitrile functional group, which is the C triple bond N functional group. So essentially what's going to happen here, if we look at the reaction below, is that if we have an aldehyde or a ketone, so we have aldehyde in the bottom, ketone at the top, the oxygen that takes part of the carbon-oxygen double bond in the carbonyl group is going to get reacted with, or it's going to get messed with. The oxygen is going to undergo a reaction where the double bond, or the pi bond, should I say, in the double bond is going to break. So we have the double bond here. One of these bonds breaks, or the pi bond, and if we want to look at the orbitals, is going to break. And what's going to happen is that a cyanide, a CN group, is going to be added to the carbon where that double bond ends with, or reacts with. The oxygen in the carbonyl will still be preserved, but a hydrogen will be added to it. So in the hydroxynitrile we see here, which has both the hydroxyl group, the OH group, the alcohol group, and the nitrile group, the C triple bond N, that oxygen in the alcohol is actually the oxygen from the carbon-oxygen double bond. A hydrogen gets added to it, and then the cyanide, the CN, comes in and gets added to the same carbon, giving us our hydroxynitrile. So this is the hydroxynitrile we talked about. The carbon in question, which is a carbon of the carbonyl group in the aldehyde or ketone, is going to have both an OH and a CN group. Now, one of the things about this reaction is that the cyanide that reacts, the hydrogen cyanide that reacts in this reaction, has to be made in situ. And if we remember from prior chapters, in situ means on site, meaning that we are not going to add hydrogen cyanide. We're going to add two reactants that create hydrogen cyanide. And those reactants are potassium cyanide and sulfuric acid. When potassium cyanide and sulfuric acid react together, they react in a 2-to-1 ratio to create the hydrogen cyanide that we need for the reaction, and also potassium sulfate. So when these two react, they create the hydrogen cyanide, and then the hydrogen cyanide can go in and react with our aldehyde or our ketone to create that hydroxyl nitrile group. Now, this is a nucleophilic addition reaction. Why is it an addition reaction? Because remember, these have two parts. The addition part comes from the fact that we are breaking a double bond and adding both a cyanide, HCN, to the carbon side of the double bond and a hydrogen to the oxygen side. Remember, in addition reactions, we break a pi bond like we did in the alkene addition reaction, and something's added to both sides of the pi bond. Well, in this case, we break the pi bond on the carbon-oxygen double bond, a hydrogen gets added to the oxygen to create us that hydroxyl group, and then the cyanide gets added to the carbon, giving us that nitrile group, therefore giving us our hydroxyl nitrile. So this is a very, very useful reaction. We'll see why in a couple of slides. But one other thing that I should point out is that this reaction does need to happen in heat, meaning this reaction does need to be heated as a condition for the reaction to work. So one of the conditions for this reaction is heat. And it does, again, create a very useful hydroxynitrile, and we'll see why that's useful in a couple slides. But before we talk about its usefulness, let's talk about its mechanism, because realize that addition is the type of reaction. And this is something that we talked about in chapter 14, but it's worth re-mentioning here. Addition is the reaction type. Nucleophilic, on the other hand, is going to be our mode of action for the mechanism. So the mode of action is nucleophilic, the type is addition. Nucleophilic addition, therefore, the whole thing, is our mechanism. A mechanism needs both a type of action, whether that's nucleophilic, electrophilic, free radical, and a type of reaction, addition, substitution, elimination, etc., etc. So, the mode of action here is nucleophilic. The type of reaction is addition, like we discussed, because the atoms are being added to both sides of the double bond. So let's go into how this reaction works, the mechanism of this reaction. Nucleophilic addition reactions, like the name implies, are going to involve a nucleophile here. They're going to involve a nucleophile, which is going to be, remember, negative in charge or partially negative in charge. And they're going to have somewhere in them a lone pair. So they're partially negative in charge and have, or negative or partially negative. So it's either partial or full negative and a lone pair of electrons. In this case, in the nucleophilic addition mechanism for the reaction with hydrogen cyanide, the cyanide ion is going to be our nucleophile. We have both the lone pair of electrons on the carbon and the negative charge on the carbon that makes cyanide a very good nucleophile. So like with every reaction, a nucleophile does need something to be attracted to. What this particular nucleophile is attracted to is the carbon on the carbon-oxygen double bond of the carbonyl group. Carbonyl groups are polar. They have a partial negative oxygen and a partial positive carbon. That partial positive carbon, being positive, is what our negative nucleophile is going to be attracted to. So this is going to be a match made in heaven. Our nucleophile is going to be attracted to that partially positive carbon. So what's going to happen here is that the first step is going to involve what we call the nucleophilic attack. The carbon in the cyanide is going to use its lone pair of electrons to attack the partially positive carbon. So this is the nucleophilic attack, where the cyanide attacks the carbon to carbon attack here. And that is going to cause the pi bond in our carbon-oxygen bond, in the carbonyl bond, to break heterolytically. So the attack breaks the pi bond heterolytically, giving the 2 electrons to the oxygen, which is going to create a negative charge and therefore an intermediate. So step 1, cyanide nucleophile is going to attack the partially positive carbon, creating a bond to it from its lone pair. Remember, in mechanisms, those curved arrows showing the flow of electrons need to start at electrons, so either from lone pairs or bonds. So the carbon in the cyanide is going to use its lone pair of electrons to attack the partially positive carbon in the carbonyl group, which is the nucleophilic attack. And then that causes the carbon-oxygen pi bond in the double bond to break heterolytically. Both those electrons, and again, this is starting at the bond, are going to be given to the oxygen. What this does is that it creates our carbon-carbon bond between our cyanide and the carbon. So this right here, oops, let me make that a little bigger. So this attack right here creates a bond, which is this bond right here between the nitrile carbon and the carbon that used to be in the carbonyl group. And then the carbon-oxygen bond, pi bond breaking, and those electrons being given to the oxygen, mean that the oxygen has an extra pair of electrons and therefore a negative charge. So this creates a negatively charged intermediate. That intermediate is very reactive because of the negative charge on the oxygen. And then what's going to happen is that if there's another hydrogen cyanide molecule floating around, the negative oxygen is going to want to get rid of that negative charge. And so it's going to use its lone pair of electrons that it just gained from the pi bond breaking in order to attack a hydrogen in the hydrogen cyanide molecule. That will cause the carbon-hydrogen bond to break heterolytically, giving the lone pair of electrons to the cyanide, and essentially turning this oxygen, this oxide, the O minus, into an OH. And that cyanide, the hydrogen cyanide, will just turn into a cyanide. So in this second step, that negative charge we have on the oxygen causes the oxygen to use its lone pair of electrons and steal the hydrogen from a hydrogen cyanide molecule that's floating around and break the carbon-hydrogen bond heterolytically, recreating a cyanide ion. And then that oxygen will get a hydrogen, which is where we get our hydroxyl group from the hydroxynitriles from. So this is, again, a two-step mechanism, very, very similar to the addition mechanism we saw in alkenes. A few key differences. The mechanism we saw in alkenes was electrophilic addition, whereas this is nucleophilic addition. The main differences is that we have a nucleophile to start with instead of an electrophile that's attracted to a partially positive charge instead of the negative of the double bond. And then the other difference is that whereas in electrophilic addition, we have a carbocation as an intermediate, a positive ion. With nucleophilic addition, we create a negative intermediate in the form of this O minus intermediate. So that's the mechanism for a nucleophilic addition. And it's one that you should remember because you could be asked to draw it out in your AICE exam, in your paper 2. Now, I did mention that this is a very useful reaction. Why is this a very useful reaction? The reaction with hydrogen cyanide with an aldehyde or a ketone is going to introduce a nitrile group. And nitrile groups are very useful to introduce because they are adding a carbon to our compound. A lot of the times in chemistry, when we're trying to make different organic compounds, we'll find that the compound we have and the compound we want are off by one carbon. So if we look at the example we have down here, let's say we have this compound right here, and we want to make this compound. Well, let's say we have the compound this came from, which will be 1, 2, 3, 4, 5, double oxygen. So let's say we have this compound, right? And we want to eventually make something like this. Something you might have noticed that this compound has 1, 2, 3, 4, 5 carbons, whereas this compound has 1, 2, 3, 4, 5, 6 carbons. If you are ever in a situation where you're being asked to produce a chemical that has one more carbon than the chemical you are starting with, the easiest way to add that carbon is to do a reaction where you add a nitrile group, because the nitrile group will add that carbon for you. So we can go from this aldehyde to this hydroxynitrile by doing the reaction, the nucleophilic addition with HCN, to produce a hydroxynitrile. But that adds the carbon. However, that does not give us a usable carbon. The carbon in the nitrile is triple bonded to a nitrogen. So how can we turn this hydroxynitrile into a useful compound? Well, that's where the hydrolysis of the nitrile groups comes in. Any compound, and it's not just hydroxynitriles, but we're going to use the hydroxynitrile as an example. Any compound with a nitrile group can be hydrolyzed. So if we react that nitrile group in the hydroxynitrile and any compound with a nitrile on it, if we react that nitrile group with either dilute hydrochloric acid or dilute alkali like sodium hydroxide, we can hydrolyze it. And again, this is not be anything new. We talked about hydrolysis earlier and how it can be carried out with either acids or bases. So we can do this with hydrochloric acid or with the alkali like sodium hydroxide. But we do need to heat up the reaction. So our condition will be reflux. We need to reflux this, and we use reflux because, again, the boiling point of nitriles are usually pretty low, so we don't want it to evaporate. So we have refluxing as a condition, and we have either a nitrile with a hydrochloric acid or a nitrile with a dilute alkali like sodium hydroxide as our reactants. What that's going to do is that it's going to hydrolyze our nitrile group. Remember, the term hydrolyzed comes from the fact that we're breaking this apart with water. Hydro means water, lyse means broken apart. Why is it being broken apart? It's being broken apart because the carbon-nitrogen bond in our nitrile group is being broken. This right here breaks apart. Oops, let me make this a little thinner. The carbon-nitrogen bond, the triple bond that we talked about, gets broken apart. So if we zoom in on this, it will be a carbon triple bond nitrogen. And then that carbon triple bond nitrogen is being broken off. And then that carbon is being turned into a carboxylic acid. The product of the hydrolysis of a nitrile group is always going to be a carboxylic acid. So the carboxylic acid that we create is the result of using either an acid or a base to break apart the carbon triple bond nitrogen. So we can see here, and let me clean this up a little so it's a little easier to follow. So let's get rid of this and this. So we're going to break apart our carbon triple bond nitrogen, and I'm going to highlight a few things so we can follow them around. So our hydroxyl group stays the same. Notice how the hydroxyl group does not change. Whether we use the acid or the base route, the hydroxyl group remains unchanged. What's going to change is our carbon triple bond nitrogen, our nitrile group. That carbon in the nitrile group gets turned into the central carbon for a carboxylic acid. So if we use the acid, that carbon gets a double bond oxygen and an OH added to it, giving us this carboxyl group right here, or carboxylic acid, sorry, group right here. If we use the base, we'll get the same carboxylic acid carbon, so carbon double bond oxygen O, but it'll be an O minus. Because, again, and the carboxylic acid cannot exist in basic conditions. It exists as a carboxylate ion. And then that carboxylate ion can be acidified with sulfuric acid, or really any acid, to give us the carboxylic acid. So what is getting reacted here is that carbon triple bond nitrogen. And it's getting turned, the carbon that is originally bonded to nitrogen is getting turned into the central carbon for a carboxylic acid. And that's why this reaction is so convenient, so important, because then we can grab the carboxylic acid and we can react it in different ways, like reducing it to get other compounds, like alcohols or aldehydes even. So this is a way of adding a carbon to a carbon chain. And we can do that with an acid with reflux or with a base with reflux. Again, if we got the acid, we go straight from the nitrile to the carboxylic acid. If we use the base, we go from the nitrile to a carboxylate ion. And then that carboxylate ion, if we add a little bit of an acid, can be turned into a carboxylic acid. So that's why this reaction is important. It's very useful for adding carbons to starting materials that don't have the necessary number of carbons. And that's it. That's it for section 18.4. We'll keep looking at other ways in which we can react and test for aldehydes and ketones in the next video. Until then, see you soon.